He's at UC Berkeley, Department of Statistics and International Computer Science Institute. He's focused on large-scale machine learning, including randomized numerical linear algebra and regularization methods. He's a professor from Yale, or got his PhD from Yale. So please help me welcome Michael Mahoney.
This is a meeting Greg mentioned. So this will be running in Berkeley the 17th to the 20th of June this year. And so what I'll be talking about tonight is implementing matrix algorithms in large parallel distributed environments. And so this meeting actually started out trying to address some of these ideas. My PhD, as I said, was in statistical mechanics and did a lot of just implementing various quantile, algorithmic, a lot of numerical implementations and applications of numerical. Then I switched to theoretical computer science and did a lot of work on the theory of matrix algorithms. And it was clear that there was a huge impedance mismatch between the two areas. And that a lot of the ideas in theory could be useful in practice but weren't. And at the same time, if you just took the practical ideas and sort of modified them locally, you're sort of overfitting or over-optimizing to the infrastructure that existed. So we decided to start these meetings in 2006, just really talking about matrix algorithms. A lot of graph algorithms and machine learning boil down to matrix computations of one form or another, and the spectral graph ideas and whatnot. Really to focus on the matrix algorithms, the test case for sort of establishing algorithmic and statistical foundations for a lot of large-scale data problems. Not from the perspective of scientific computing or PDE, that sort of thing, where a lot of the development's been done, but maybe draw strength from those ideas and apply it back to a lot of large-scale data analysis of machine learning. So some of the themes in the talk today will appear here again, so if anyone's interested in this, it would be great to see you for another later in the month. I'll be around afterwards if there's any questions. Yep. Not online streaming. We were, with high probability, we're recording the videos and we'll post it online the way we did last time. So you can see videos from last time online, but it's not going to be streamed online. Meaning in real time. So it'll be up a couple weeks later. All right. Any other questions? All right. So what I'd like to talk about today is actually sort of delivering on the promise. So I started MMDS back in 2006 to say, geez, these theoretical ideas, are interesting and could be useful, but they aren't yet. And when you have sort of a fundamentally new way of designing algorithms and doing something very differently to have done it, it takes a while to work out the kinks and be competitive and keep the state of the art. And so what I'd like to tell you about now is sort of a progress report. It's 8 years later, but a couple of these results have been around for a year or two, so 6 or 8 years later. And the idea here is we want to use regression algorithms. Use regression algorithms to think of over-constrained least squares or least absolute deviation. So it's not true that if you're interested in principal components analysis or SVs or these sorts of things, it boils down to regression problems. It is true that it almost boils down. All right, so I'm going to talk mostly about this. There are some technical things that are interesting about going to fat matrices when both dimensions are large, and I'll sort of allude to that. But for most of what I'm talking about is regression algorithms. And talk about sort of implementing them at large scale, and if you're going to go to large scale, you need to worry about parallel distributed issues. So what? So here's sort of the high-level idea. So if the data is small or medium, whatever that means, a not uncommon way to think about the data and to model the data is as a matrix or a graph. You have n data points described by m or d or p or whatever this variable is, depending on what area you're from, number of features. And when you do that, you're thinking about data typically in a Euclidean space. And sort of a natural thing to think about in a Euclidean space is eigenvectors and correlations and these sorts of things. And typically are small enough that you're in RAM. And a lot of scientific computing has really gone to a lot of effort to hide the fact from you that there's a memory hierarchy and stuff going on. So it looks like things are in cube time. It's been very successful. When you get large scale, meaning sort of very, very large scale, the situation is probably like, just very different. Typically, you'll model the data. It's a data model. The data is just whatever it is. Right? It's fixed it's images or whatever it is. You model the data by a flat table. It's a big database. So it's a flat table, and you'll have your relational model, and you'll think about computing with joins and selects and these sorts of things. And these are much more sort of basic and much simpler type of operations. on the data than eigenvectors and correlations and exact orthogonality. So a question, and it was a promise you made back in 2006, but it wasn't clear you could deliver on it until you finally do. But question: in some sense, can you bridge the gap and do what I'll call vector space computations at very large scale? And there's a lot of deep details here. There's going to be precision parameters and a range of things like that that I'll get into. But sort of at a high level, it's not obvious that the answer is yes, right? I mean, exactly computing eigenvectors and correlations and so on is fairly subtle, actually, if you know the details of how codes work to do that. And in particular, it's going to use a lot of communication. On the other hand, the answer is not obviously no, because we've done a lot of work in the theory of matrix algorithms, randomized, numerical, linear algebra, that basically involves random sampling or random projections. And random projections are just random sampling from a random basis, where the non-uniformity structure is flat. And so it's not obviously no, because one of the lessons from this whole area is that you can get epsilon close with using very small samples, where epsilon is 0.1. If you want to make epsilon 10 to the minus 2 or 3 or 10 to the minus 10 or minus 15 machine precision, going that last little bit from 99 to 99.9999% takes an awful lot of effort. But if you want to get pretty close, you can do it pretty easily.
Should I save questions for the end?
No, either. But
so could this also be used for avoiding overfitting? So since they're talking about sampling, not necessarily because I can't fit in my machine, but because I don't want to use the whole skew that I have in my data set. I just want to sample from it.
So I'll give you the short answer, and if you're interested, we can talk more offline, because I'm not going to talk about that today. So most of the theory here is in the following form. It takes such and such time to solve the problem exactly, where exactly means numerical precision or whatever, and if you know that, that doesn't mean exactly. They take machine precision as exact. It takes such and such time to compute the problem exactly. Theorem. We can solve the problem faster than exactly, and we're only epsilon worse. Now, that's sort of a computer science or worst case type of theorem. Now, you might think, geez, I'm not exactly solving 10 digits. Maybe I'm not exactly fitting to all the noise in today's data, and I'm going to be a little more robust to tomorrow's data, which is what you're getting at. And that could be true in general, but in particular, because these are going to be randomized matrix algorithms, there's going to be random bits floating inside the algorithm. So the theorem, I said, is going to hold true and there's random bits inside the algorithm, but you might say, geez, the fact there's random bits inside the algorithm means that I smudge things out a little bit. And one of the benefits of that is exactly what you say. Now, you've seen that empirically in a lot of cases. Characterizing that theoretically, characterizing the implicit regularization sort of inside worst-case algorithms is a challenging thing. We don't have a nice, clean characterization of it in this application. We do have a nice, clean characterization of it in some other applications having to do with diffusions on graphs and computing eigenvectors in different ways. So, nice open problem. Can you characterize that? But definitely the answer is yes empirically.
Is all this just for static data sets, so like not for streaming?
Some of this can be extended to streaming. So the basic stuff I'll be talking about here is static. You're either in RAM or you're on a bunch of machines, not in RAM, so the communication is going to be expensive and computation is not. Problem, I have a matrix, it streams by me in a way. Can I compute leverage scores? Can I compute other things that are under the hood inside these algorithms that are important to make the algorithms work? Can I get a low-rank approximation in streaming? The short answer is yes. The long answer is there's a lot of details and things, and I'm not going to go into that as much. But one way to think about the parallel distributed is you can make a pass over the data, and so you allow yourself to stream through it several times, and the passes is the expensive thing. If you want to get very greedy, you could say, geez, what if I can only pass over it once or twice? And there the answer is still yes, but it depends on details of the way the data is presented. Is it arbitrarily, is it row access, and if it's arbitrary, do you present the data element all at once, or do you increment it plus minus 1? So the short answer is yes, it can be extended, and the long answer is there's still a lot more work to be done there.
So is there like a streaming formulation for PCA or GWA or something?
I mean, a question could be, I'm given, you need to specify exactly how the data is presented. One way is to say the data is going to be presented I, j, aij, in arbitrary order. All the non-zeros, you could throw zeros in there also. What's the problem you want to solve? So asking to solve the best rank K approximation to the SPD or the best rank K approximation to the PCA is in fact not a well-posed problem. Because if you tick the one node on the other side of the universe, the K and K plus first eigenvalue can shift. And so then what do you do? So a lot of numerical analysis, when I was saying you don't solve the problem exactly, the 10 precision sort of exactly, gets the details like that, because those actually make a lot of difference. So you have analogous issues in the streaming setting, but they're a little bit different. And so you need to ask the question in sort of a robust or well-conditioned way, and they're a little bit different. So that you can do that, but modulo those sort of lines. All right. So why randomized matrix algorithms? So the question, we learned a couple of these things. So traditional matrix algorithms, think direct and iterative methods, interior point methods, simplex and so on, designed to work in RAM. And at the end of the day, the performance is measured by flux. Matrix vector multiplies. Dense matrix vector multiplies. Don't think sparsely in algebra. A lot of work done there too, but dense matrix vector multiplies. And they're not particularly well suited for a range of things, problems that are very, very large, distributed or parallel. When you're distributing parallel communications, oftentimes the bottleneck, when the data has to be accessed via passes, either streaming or several passes. So randomized matrix algorithms are faster, better theory. You can solve least squares regression qualitatively faster than algorithms that existed 5 years ago using randomized matrix algorithms. Both dense cases and sparse cases, worst case theory done. That's actually a remarkable result. Unless you don't care about the theory, you care about the practice. Simpler and easier to implement. That's nice because you don't have to worry about pivot rule decisions as much. Implicitly regularized, this gets to the question that was just asked. Inherently parallel and more scalable. So more scalable in what sense? So more scalable and parallel distributed, we'll get to that today, but more scalable in RAM. If you want to go head-to-head with LAPAC and ask how well does an algorithm work on clock time, the 10 degrees of precision, these will also perform well there, and I'll give you an example of that. So it's good in a bunch of senses. So a little bit more detail. So traditional algorithms, think, there's a complicated space, but think, you're going to use something like a direct method. So people are taking pictures of this, that's fine. These slides in various forms are also up on my webpage. So pull down something with the same title or similar title, and you can get all the slides, but it's okay if you want to take pictures too. These slides will be available, or are currently available on my webpage. So think direct methods, QR, SVD, normal equations. It takes such and such time. No iterations are saying it takes such and such time. Pros, high precision, it's implemented in LAPAC. Cons, it can be hard to take advantage of sparsity, tricky to deal with parallel environments and so on. Iterative methods. So if you know nothing about iterative methods, you probably know about something called conjugate gradient. Are there other iterative methods? Conjugate gradient is a function of communication. So it wasn't obvious, but it turns out there are, and they'll be important. You can get approximate solutions. If you want 2 or 3 digits, you iterate. It's not quite digits because it depends on the spectrum decays. You can iterate some number of steps. How many steps do you need to iterate? Who knows? That depends on something called the condition number. It's a problem-specific complexity measure. So you need to iterate a number of non-zeros times something related to the condition number. And it can be hard to predict the number of iterations, A priori. L1 regression. So we're going to be talking about tall matrices, over-constrained regressions. L1 regression is, in a sense, a harder problem. It's a linear programming problem. So AX minus B with the Euclidean norm on the residuals. L1 regression is AX minus B with the 1 norm on the residuals. Interior point, simplex, ellipsoid methods. So if you're theoretically inclined, you like the ellipsoid method because it has good theoretical properties. No one else cares because it's not particularly useful in practice. So we're going to be using the simplex method or interior point methods. Why is that? Is that because of computation, or is that a fundamental issue? I'm committing with this after that. And if we don't, I forget to say it, remind me to kind of underline mention the ellipsoid method here. And a lot, you can do relatedly squares, so iterative relatedly squares. First order methods, a range of things. You can apply stochastic gradient stuff to that if you want. Hopefully, it's also more general. So at a high level, think sort of nearly all traditional algorithms for low rank problems, continuous optimization, et cetera, boil down to something like this. All right? So it's really talking about regression and over-constrained regression. Fair question. How do some of these ideas extend more generally? We have results along the way. I'm going to talk about those today, but I can mention afterwards if anyone's interested. So here's the notation, and once I took them out, I think I changed it halfway through the talk, but I'll show you where it is. Since it doesn't matter, because if you understand that there's a high dimension and a low dimension, you're done. You can call it different letters. If you're a statistician, you might use different letters, or a computer scientist, but matrix A, it's M by N, or N by P, or M by D, or whatever, but there's a high dimension and a low dimension, over-constrained. There's a right-hand side vector B, and you want to fit AX equals B. So in general, there's not a solution X such that AX equals B, if you're tall. And so there's many more constraints and variables. And so you want to get the best such vector X, that AX is supposed to be. And one way to quantify best is that there's some norm of that residual, and you call it P, and that P can be 1 or a 2, or so 1 or 2 is the most common. Could be an infinity number. 1 or 2. So P equals 2 is least squares. All right, very, very widely used. Can be sensitive to outliers. P equals 1 is called least absolute deviations. All right. Better robustness properties. but cost of increased complexity. Here's an L1 on the penalty. If you're familiar with L1 on the regularization term, that's a related but different issue. We'll not be talking about that today, but I can mention afterwards some of the ideas related to that. But this is L1 on the objective, and we're over-constrained. Some of the ideas will extend on their constraint, but today we'll be talking about over-constrained. Actually, a lot of the ideas will extend, but not all. So why over-constrained? So there's a lot of examples, where you're, whatever, SNPs. 1,000 people, million SNPs, actually. One of the pictures I'll show you is data like that. Pixels in an image is 1,000, and you have 100 million images. Natural language, if you look at singletons, not so much, but if you start to look at bigrams and trigrams, you get much higher. More generally, I think over-constrained L1 and L2 regression, if you think about developing algorithms for large-scale problems, it's a good model for implementing a wide range of other matrix algorithms, basically because the basic ideas underlying them extend much more generally. So a lot of other sort of examples of large-scale sites, right? So large-scale environments. So this is sort of a complicated landscape. It depends on your background and whether you work in a government lab or an internet company that has a million CPUs and wants to tie them together in a way that's robust to individual node failures, or whether you had a company that wants to have a million nodes but doesn't. I mean, it depends on a lot of things. So roughly think of it, you're in RAM, meaning things are sort of small enough that you can put the memory footprint in RAM. The memory footprint's not going to be the problem. The problem's going to be accessing the data in various ways, with pivot rules and so on. So well before you have a memory footprint problem, you have a problem like that. But you can get larger in terms of memory. And then roughly you're in one of two situations. You either have sort of in an environment where you may have a supercomputer or something like that, and then a lot of work sort of influence from scientific computing and message passing and these sorts of things is the way people think about it. A different thing is that you're in a distributed data center. Communication between the individuals is very expensive, and so you want to minimize that. So that's one of the most expensive things. So roughly that's the landscape. And I'll give you an example of each. And in fact, merging that landscape into something that a lot of people kind of do. So what I want to first talk about is RAM. All right? Because if you understand the basic idea, how do you extend it not to RAM? Do the same thing, but worry about communication and not computation. All right, so this is going to be this is randomized numerical linear algebra. So think of it as linear algebra, but with a heavy dose of randomization in it. So it's just a very different way to think about matrix computations. Another very different way to think about matrix computations is something like stochastic gradient descent to do various sorts of optimization. And this is a problem that by now is sort of bread and butter of machine learning, Robert used a lot. 10 or 15, I don't know the exact number of years ago, optimization people they still hated it, and said, well, you get low precision, and this problem, that problem, that problem, that problem. And machine learning said, yeah, but low precision is fine because it gives you implicit regularization. We don't want 10 inches of precision. You can distribute and parallelize better, and so on and so forth. So think of it a little bit like that. You can do stochastic gradient in RAM, and you'll get results, but it's really useful in a range of other contexts. So same sort of thing. So I'll talk about it in RAM to give you the basic ideas and show you something, and then I'll illustrate how the ideas are generalized. Question: how does randomized linear algebra compare with stochastic gradient descent? I was hoping actually to have the results to show you. We have actually the first sort of combination. They have complementary strengths and weaknesses, both technically in terms of the form of results you get, but also sort of how they're used. And you can take the strengths of both and get something that's better than both. And we have a clear proof of principle of that, and maybe in a year or two I'll figure out to tell you more about that. But we didn't get those results done in time, but you can combine the two later. All right. So we're a small matrix, we're in RAM, but again, these results will generalize if you worry about communication and not computation. Okay. So how are you going to solve this over-constrained least squares problem? So let's talk about L2 for now. These results will generalize to L1 in mathematically, technically non-trivial ways. The implementations are sort of similar, so they're not very, very different. You need to call different areas and so on, but they're not so different. So the intuition I think most people have is probably better for L2, so we'll talk mostly about that. There's two things you need to know to sort of get good algorithms here. And these are both problem-specific complexity measures, all right? So we don't want some theoretical result that says either for every matrix, or I'm fast in such and such way, or I'm fast in such and such way, depending on a parameter that depends on the input. So what do you mean by that? sort of an absolute result I'm fast in such way is what you get with direct methods. Here's a matrix, run n cubed computate steps, and you're done. An iterative algorithm says I'm fast in such and such way with a problem-specific complexity parameter. I need to do a matrix vector multiply, so that depends on the number of non-zeros in the matrix. And how many times do I need to do that? Something that depends on the condition number. All right, so there's two problem-specific complexity measures. The more well-known is, in fact, the condition number. And if you ask, what is the condition number? Condition number is about eigenvalues. The condition number is a ratio of the maximum to minimum eigenvalue. Sort of informally, you're doing L2, or you think about it having a quadratic well with some aspect ratio. That condition number gives you these max to min stretch of that quadratic well. All right, so if that well is a nice circle, it's easy to iterate, and if it's very, very elongated, it's hard to iterate. That's the basic idea. So the condition number is the ratio of the max to min, and it bounds the number of iterations you need to do. Now, computing it is generally as hard to solve the least squares problem. So generally, you can't compute it. Sometimes you can estimate it, sometimes you can know it because of modeling results, but computing it for a given matrix is as hard as solving the problem. But it's about eigenvalues. So a very different type of complexity measure is about eigenvectors, called statistical leverage up top. The statistical leverage scores, assuming we're tall again, if you're tall, the projection matrix onto the high dimensional space, what does that look like? All right? So the projection matrix onto the high dimensional space can be written as, let's call it UU transpose, if U are the left singular vectors. So in a sense, it's a projection matrix onto a low dimensional space, but formally you're up on a high dimensional space. Now you can ask yourself, what is that projection matrix? So I said it's UU transpose. You can think of that as a tall orthogonal matrix U, and you can say, what are the Euclidean norms of the rows of U? The columns are unit length and orthogonal, but what are the Euclidean norms of the rows? Now these Euclidean norms of the rows are the diagonal elements of the projection matrix. The dot product between two different rows of the off-diagonal elements. These are the diagonal elements of the projection matrix. So let's call these leverage scores, just definition. They measure how well correlated the singular vectors are with the canonical basis, not how much is that quadratic well stretched, but given whatever stretch factor that is, where does that sit relative to the canonical basis? If you think of it from a statistical perspective, it measures which constraints have the largest influence. So if you're a statistician who's done regression diagnostics, these are the diagonal elements of the hat matrix. Right? So you can use them for regression diagnostics. They measure a notion of coherence and outliers. If you hear people talk about making assumptions about coherence, coherence is an infinity max over this vector. And computing them exactly is as hard as solving the least squares problem. All right? The leverage scores are what you need to deal with to get low precision, top right in the red. Right? If you want a low precision solution, you've got to deal with them one way or another. You either find them, or you uniformize them, or you dance around them or something. But you got to deal with them. And the condition number is important for high precision. You either need to iterate a lot, or you need to get a preconditioner such that you don't have to iterate a lot or do something else, but you got to deal with it. All right, so that's going to be the main idea. So here is sort of a meta algorithm, a high-level idea, is following. So tall matrix A, compute the L2 statistical leverage scores of A, some way, exactly or approximately, and construct an important sampling distribution with them. Just normalize them so they're complete. Then, randomly sample a small number of constraints, using those scores as an important sampling distribution. So I told you these things are outlier measures. You're biasing yourself towards outliers. It's your job as a data scientist to clean up the data. If you give me, algorithm, you give me garbage, I'll give you garbage back. Okay, so it's your job to clean up the data. Once you clean it up, you give it to me, and I'm saying, I'm going to bias myself towards the thing that are outliers. Solve the L2 regression problem on the solve problem. All right, tall matrix, compute an outlier score, bias yourself towards that, randomly sample a small number of constraints according to that, solve the subproblem. If you do that, you'll have a 1 plus epsilon relative error solution. Very, very good solution. On the objective function, on the certificate, on everything. Very good solution. Now, a naive version of this algorithm will give you 1 plus epsilon solution, and it will run in m times n squared divided by epsilon time. So m times n squared is a straw man, right? That's QR. Epsilon, the 1 over epsilon might not be so bad if epsilon's 0.1, but not so good if epsilon's 10 to the minus 16. But do you understand this? There's got to be someone out there who doesn't understand this. All right, if you understand this, we'll be able to dance around all these issues. But you have a tall problem, all All right, this will extend to fat problems if we use rank parameters and so on. If there's a high dimensional space and a low dimensional space, find data points that are outlying, randomly sample a small number of constraints according to that outlying score. Solve the subproblem.
Question?
Yeah.
What is the intuition behind that method that the other constraints won't be violated? We didn't even look at them, so does the outlier take care of that, or how did you take care of other constraints not getting violated?
So by constraints, I mean rows of the matrix. It's not a constraint least squares. This is different areas use the words in different ways. So by constraints, I mean rows of the matrix. It's not a constraint least squares, so it's not like the other things would be violated. Now, it is the case that if I get an x opt, an optimal x, and I plug it into those other things, you know, that particular residual value might be worse. But it doesn't matter, because the only thing you care about is the sum of squares of all those residuals. You don't care about any particular one. If you cared about any particular one, say the largest, you should be doing L infinity or something else. So least squares means you don't care about it. So it's okay to make that any one particular one worse.
So there's something you are preferentially something for it to be algebra.
Correct.
Can you repeat that question for the video?
Yep. That's okay.
This
No, we finish it at all.
when you are doing physical analysis, will be actually concerned for the final
So the question is, I'm up here telling you to bias yourself towards points of high leverage. Typically in regression diagnostics and statistics, you worry about data points that have high leverage, and I'm telling you to bias yourself towards it. So first of all, if you're doing a random projection or any of a bunch of things people do, you're doing this, you're just hiding this fact. You're rotating to a random basis where you're doing this. So I'm just making it explicit. You can't blame me for being honest. That's the first point. The second point is, if you want to understand sort of how other people and statisticians think about these problems, it's actually in just two very different ways. And you know, why do people run least squares? A statistician would say a person should run least squares if such and such Gaussian priors and so on and so forth are assumed. Of course, no one ever, sometimes people check that, but whether or not it's satisfied, people are going to do least squares anyway, or SVD. And think of it as the extension of SVD. Think of LSI, latent semantic analysis applied to term document matrices. And these things are incredibly sparse, which means there's Gaussian assumptions that go in there, right? Or SVD applied to DNA SNPs. And each SNP is a single event in human history. Who thinks there's something Gaussian about that? So people apply SVD and PCA in situations where the statistical assumptions are just sort of manifestly violated. In those cases, it's not implausible to say, gee, since I'm running computations that sort of implicitly assume a model that I know is wrong, it's not totally implausible to think that there might be data points that are outlying relative to that model. And in that case, those data points might be the most interesting ones. And in fact, sort of that's the case. So that's one answer. The other answer is the one I gave before. It's your job to clean up the data. It's my job to give you an algorithm. LA-Pac will give you an answer even if you ask the wrong question. So this gets, yeah, so there's a bunch of answers, but they're also in that space.
So this seems remarkably like just important sampling in Monte-Carlo method. Just that it's applied to the...
It is important sampling. So when you say important sampling in Monte Carlo, the way it's used in a lot of applications is you have a state space that's exponentially large. You want to sample from a point with probability proportional to some important sampling value. You can't touch the whole space and you want a Markov chain. So this is not Markov chain.
This is like sequential Markov chain.
No, it's not Markov chain. If the state space is exponentially big, the ball game is to find a point that's more than exponentially small probability, right? You know, where all your energy is in the physical configuration or something. Here, the state space isn't exponentially big; it's a size m inside m rows. So it is important sampling, but it's on a polynomial, in fact, linearly big space. So you don't have to run the Markov chain, but it's the same idea. All right, so randomly sample high-level leverage constraints. The idea is that if you have a line and you say which of these points is the most important in terms of influence of least squares fit, it's going to be this one out here. You better find that. And again, it's your job to process the data such that either it's there and it's acceptable or not. Here's a particular application. If you're in genetics, the geneticists would pull those off and say those are the most interesting ones. By their downstream metrics, they don't know or care about this one in theory. If you're a statistician, there's the average, and you say, geez, I want to flag a data point if it's 2 or 3 times above the average, and see it go to there. So everything above that line is an error, is an outlier, is garbage, if you go with that sort of traditional measure. And This is not all uncommon. See this sort of thing in a lot of applications.
So how did you actually compute the leverage something you said that was the same or the...
So we'll get to that. One answer is just compute it. So that's not going to solve the large scale problem, but you might be interested in actual columns, actual DNA SNPs. The geneticist isn't interested in eigenSNPs, the geneticist wants actual SNPs. So it's not the least squares problem I'm talking about for the extension of matrices. You might just be interested in that, compute it. Or you can compute it away, I'll tell you in a second. All right, so you're over-constrained, you choose a small number of constraints, apply it to the high algorithms, you get a small subproblem, done. Okay. Now let's make this practical.
So the leverage is just the norm of the row, is that correct?
The leverage is the norm of the row.
Yeah.
Yeah, I have a matrix A, and I do QR, or this could be U, and this is sigma B transpose from the SVD. It's the Euclidean norm of that row. It's maybe squared, but yeah. The Euclidean norm of that row, QQ transpose, is a projection matrix. The diagonal elements of that projection matrix is that row dotted into itself.
Is that a good definition of leverage? Are there alternative definitions of leverage?
There's a bunch of notions of leverage and influence in statistical regression diagnostics. Almost all of them are this or sort of a cousin of this. It depends on which space you're in and some other things. There are other notions. We haven't gotten them, we haven't thought about them as much. We haven't gotten them to explore them algorithmically, but there are some other notions. Typically they come with some unlegal guarantees. All right, so that's the meta algorithm. How do you make it fast? In RAM, we're still in RAM. So this meta algorithm can be made to run fast. So this slide is actually old enough that both of those lines are correct but have been improved. First bullet, this meta algorithm runs in mn log n divided by epsilon time in RAM. That mn log n can be made number of non-zeros. That's actually a very non-trivial result. We were talking in Woodbrook about a year and a half ago. So for arbitrary worst case input, if you fix an epsilon to be 0.1, you can compute an epsilon approximate solution to the least squares probability in 10 or 20 or whatever the constants are, times the number of non-zeros. Constant times the number of non-zeros. That's actually a remarkable result. So that's been approved, but let's talk about this one because this is going to be most relevant to the extensions I'll be talking about today. It runs an mn log n time. The matrix is tall. M is the high dimension. N is the low dimension. So you have to beat m n squared. It's mn log n. So you've beaten it. How do you do that? You can do it one of two ways. First, do a random projection. If you do a random projection, just implement, which is a matrix vector multiply, let's say Gaussian or random marker, random variable, there are a bunch of ways you can do it. Implementing that random projection is high dimension times low dimension squared time. Just do the matrix vector multiply. So implementing that. If you use fast Fourier techniques, so you don't have to use Gaussian random variables, you can use something called, basically a Hadamard transform, a Hadamard rotation, and take advantage of fast Fourier techniques. It's actually a randomized Hadamard transform to multiply it by a diagonal plus minus 1 matrix times a Hadamard. And when I say Hadamard, Hadamards don't perform the best in practice. It's some discrete cosine and hardly a range of things that are Hadamard related. You can take advantage of fast Fourier techniques. And because of that, you get the log factor in place of an n with log n. So mn log n time. If one, you perform a random projection. And what a random projection does is rotate you to a random basis where the leverage scores are uniform. Not exactly, but approximately. Sample uniform. Call that previous result done. Or call a black box, hint at what it does, call a black box that computes the leverage scores approximately. And use those approximate scores. Call the thing from a couple slides ago. What's that black box? Let me not go into the details except to say, here you computed QR. Right? If you can get Q or some approximation to Q, you're done. All right? What the approximate algorithm does is hit A on the left with a random projection, with a Hadamard-based random projection. So the running time of the second step is the same as the running time of the first step. You hit A on the left with a random projection. You construct a smaller matrix, A prime. Do QR on A prime. And then pull it back up in to the high dimension. And if you do the order of operations right and so on, you can pull up to the high dimension without incurring the quadratic factor, at least on the lead term, right? So hit A with a random projection and do QR on that thing. The Q you get there is not an orthogonal, when you pull it back up, it's not an orthogonal matrix. So it's not perfect, but it's approximately orthogonal. It's good enough. In particular, if you evaluate the row norms of that modified Q, they're 1 plus epsilon approximations to those things. All right? Approximation leverage scores, call the algorithm from a couple slides ago. Done, 1 plus epsilon solution.
So is this the GL embedding?
So all the random projections will be Johnson-Lindenstrass at the end of the day. Johnson-Lindenstrass is more general. It works in general metric spaces. So here you're applying it in Euclidean space. So you get sort of a subspace analog of Johnson-Lindenstrass and you preserve the geometry of the whole subspace. And in fact, that fast Hadamard thing is a range of projection methods that grow out of something called the fast Johnson-Lindenstrass. Allian Chazelle introduced in 2006 or something. So it's basically a version of Johnson-Lindenstrass that still gets the same distortion properties, but it's fast because of the fast Fourier methods. But it's exactly that.
No, it's cool.
Yeah. Now this is good. That mn log n can be replaced with number of non-zeros in the matrix, divided by epsilon. Not bad if epsilon's 0.1. What if epsilon's 10 to the minus 10? So I said this is what you need to get low precision. You need to get the leverage scores. Rotate to a random basis where they're uniform. Compute them approximately, do something. To get high precision, what do you need to do? You need to deal with the condition number. So to deal with the condition number, you do one of two things. You either eat it and just iterate a lot, or you construct a preconditioner. And a preconditioner is basically a way to process this problem such that you get a new problem. If you solve this problem, it has better condition number properties, so you can solve it quickly. You get a solution to this, and it's trivial to convert back to solution to. So, what you should do to get this meta algorithm to run in mn log n, or number of non-zeros times the log of 1 over epsilon, not 1 over epsilon. What you can do is one of two things. You take the random projection you did up there, or you take the random sampling that you did up there, take that basis, essentially that Q matrix, don't solve the subproblem like I told you to do. Don't solve the subproblem. Use that basis as a preconditioner. If you use that basis as a preconditioner, or, well, to construct a preconditioner, but it's true to construct a different basis, call it traditional iterative method. What iterative method it should it be? You know, whatever you like. You can use time to create it. All right, call it traditional iterative method. All right? So that's nice. How will that perform in practice? So this is Avram and Toledo, blend and pick. X-axis here is a size parameter, y-axis is 1, 2, 3, 4. So forget about nice big O's and asymptotics. This is clock time and factors of 2 and 4 going to matter. And they looked at not some nice sort of esoteric problem, but I mean, over-constrained least squares dense, and totally ubiquitous. They evaluated it on a bunch of different types of matrices, varying leverage score structures and eigenvalue structures and so on and so forth. The bottom line is blend and pick, the randomized matrix algorithm. Do a random projection, solve it directly if you want, but in particular, for high precision, use it to construct a preconditioner and iterate. These randomized algorithms beat LA-PAC's direct dense squared solver by a large margin on essentially any tall dense matrix. Right, so this isn't some esoteric problem. This is least squares going head-to-head with LA-PAC. That if you call R or MATLAB or anything, you're calling something that calls something that calls this routine. And you're beating it by a large margin, factors of 2 to 4 or whatever, on essentially any tall dense matrix. Results suggest random projection algorithms should be incorporated into future versions of LA-PAC and a number of other things. And so that's, you know, in progress. They didn't evaluate the sparse, and the short answer is I don't know. We had a result that was sparsity, I don't know what you want to call it, but it took advantage of the sparsity. The results I mentioned before about the input sparsity time projections, I'm not going to come to go into detail, but I'll mention we haven't evaluated the L2 version, we have evaluated the L1 version. And I don't know how it can scale to things that are larger than you can solve without, but that's sort of a different issue than addressing this precision issue. So that hasn't been evaluated. The other thing is the infrastructure for sparse linear algebra libraries is also very different. So, but for that, I'm going to
Apologies, Michael, I can't read it over. What's the epsilon given for these results?
for these
Yes.
machine precision, I think it was
A
a couple orders of magnitude.
Or
Yeah, I think it was a couple orders of magnitude higher than machine precision. It might have been, I want to say 10 to the minus 12.
Not 0.1.
No, not 0.1, no, 10 to the minus 12 or something like that. I don't remember exactly, but when you get right near machine precision, there's tall, skinny QR.
Understood.
There's a couple issues if you want to get machine precision or an order of magnitude or 2 above, but you're 10 orders of magnitude below 0.1. Bunch of extensions of these things to a wide range of applications. The last two things are pictures not about the regression, but extensions of these ideas to doing large-scale kernel methods in machine learning and single value decompositions in genetics and analyzing large-scale social graphs and a range of things. So let me not go into that. And bottom line, so I think it's been a big success story if you're interested in theory, big success story in large, well, sort of a lowercase l scale statistical data analysis. Can they really be implemented, applied in capital L? All right, so to do that, you need to deal with parallel distributed issues. And so I'm probably not going to talk much about the quantile regression. Now, let me look at the L2 regression first, and then a little bit more detail about the L1. Just to give you an example, but what you should be thinking is do exactly what I said, but worry about communication, not computation. So in particular, don't worry about fast Hadamard's, because computation is relatively inexpensive. Worry about communication. So LSRN you should think of as blend and pick prime. All right, blend and pick optimizes flops and RAM, competes with LAPAC. LSRN tries to do this in a parallel environment. So rather than doing a Hadamard-based random projection, 1, do a Gaussian projection, 2, construct a preconditioner, 3, iterate with some iterative algorithm. I'll get what iterative algorithm we should look at in a second, but first, why Gaussian projection? So Gaussians actually provide the strongest results on conditions, and that's going to be important because I'm going to get to in a second. So if you want to guarantee, with extremely high probability and really cover your tail, that you get the condition numbers right, Gaussians are the way to go. You can use level 3 blasts on dense matrices so they can be generated very quickly. It'll speed up automatically in sparse matrices because of the way you do stupid matrix fast multiplying. And it'll still work with an XOR reduce operation when A is partitioned thing that is tall along the larger dimension. So although it's going to be slow in terms of flops, that's not what we're worrying about here. Details, if you care about these sorts of details. So you can search on LSRN and pull down the code. There's a shared memory version. C++ is a MATLAB interface. In fact, generating the random bits can be the most expensive thing here if you're not careful. It's generating, a billion Gaussian random variables. So we use the multi-threaded, the ziggurat random number generator, naive implementation of multi-threaded dense sparse multiplications. There's also message passing version, Python. Single-threaded blast for the matrix vector, the matrix vector products, multi-threaded blast and LAPAC for the SVD. And it uses this version can use either, but in particular this one will use the Chebyshev semi-iterative method. And we'll get back to why that is. Instead of LSQR. So LSQR is conjugate gradients. Right? It's the Fagan-Saunders version. It's conjugate gradients on the normal equations, implicitly done the right way. Right? So you don't want to form the normal equations in general, but you're very careful and do the order of operations right. So LSQR is a conjugate gradient-based method. And we're going to not use that. All right. So solving real-world problems, these are a bunch of numbers that show it's going to be competitive with blend and pick and backslash operator, and EGLSD is an LAPAC routine. Sometimes these run out of memory and they take too long, and all these numbers are good. So let me not go through the details of the numbers, but on sort of, in terms of being backward compatible, it makes sense. So iterating. So we constructed a preconditioner, and let's iterate now. How do we want to iterate? So here is the sort of relevant code snippet if you're going to use LSQR, conjugate gradient-based method. The relevant thing here is, what's the cost per iteration? There's 2 matrix vector multiplications. That's a fixed footprint of computation. And there's 2 cluster-wide synchronization points. cluster-wide synchronization point is a communication problem, right? This doesn't matter in RAM if you get the pipeline right, but it's going to be a potential issue here. So 2 cluster-wide synchronization points. This is used LSQ, the conjugate gradient-based method. Let's use Chebyshev's semi-iterative method. And there are other code snippets here, and the computation is the same to leading order, but 1 cluster-wide synchronization. Now, why don't people use this in scientific computing if it's better in this sense? The reason is the strong concentration results on sigma max and sigma min are going to allow us to use this. So this basically constructs a Chebyshev's polynomial over the region where I say, here's the max to min eigenvalue. If you satisfy that max to min, the polynomial is not too bad, and it gets crazy. So if you satisfy that max to min, the polynomial is not too bad, and you can iterate, and you'll be very quick. If you're off by a little bit, the polynomial gets crazy, and you're dead. With vanilla conjugate gradient, you iterate, and if you're a little bit off, you just keep iterating away. You don't fail on gracefully. Here, you'll fail on gracefully. In most scientific computing applications, you do not have that strong control over condition numbers. But because we did the Gaussian random projection, which I told you had the extremely strong results on conditioning, we can guarantee that we're within this region. Use this method. It's been in the books for 50 years, but no one's ever used because they can't guarantee the good condition number properties. And the win in using this is that we're going to save a factor of 2 on communication. And the numbers here, you can run LSRN with LSQR, Chebyshev's semi-iterative method, over an order of magnitude. This is our RMZ2 cluster. And I say it's a factor of 2. There's a little bit overhead. It's a couple extra iterations. It's a factor of 1 3/4 or something like this. So over the 3 red numbers. All right? Chebyshev's semi will take more iterations, but each iteration is actually much faster. All right? It takes more iterations, but each iteration is a factor of 2 faster. All right? So the idea is use the same thing we used before. Use a method that's worse in terms of flux, but better in terms of communication, and that's the thing that's going to be the issue in parallel and distributed environments. All right, so let me sort of talk about L1 regression in MapReduce. So we could extend to L2. A lot of the ideas we go through would be relatively straightforward. L1's sort of a harder problem. And we can apply L1, but not the particular iterative thing I'll be talking about. We can get a low precision L1 in RAM. I'll tell you how we can do that in parallel distributed. It's basically the same thing. What if you want a medium precision? Not 10 or 12 digits, but 3, 4, 5 digits of precision, as opposed to 1. And there's going to be an interesting interplay here between computation and communication trade-off again. So, you have a matrix A. You can define an L1 well-conditioned basis. You can define L1 leverage scores. You can define L1 condition number. Think of it as analogous to L2. Don't worry about all the formalities there. Think of it as analogous to L2. It's analogous, but weak. L1 is just, not as nice a place. It's a more complicated place, and L1 regression is a harder problem than least squares. All right. So the short answer up in the top of this is everything will generalize from L1 to L2. All the subspace embeddings of regression, everything will generalize, but everything will generalize pretty messily. All right. Getting the mathematics is much messier, and the implementations are going to be a little bit messier. And the control and the aspect ratio of the matrices and so on is a little bit worse. So the L1 is a harder place. So everything will generalize. So think of the L1 well-conditioned basis in the same way as an orthogonal matrix is nice with respect to least squares. L2, a nice basis for A. That is a nice basis for A if you care about L1 stuff. And in the same way as a condition number is going to control the aspect ratio of this quadratic well that tells how many times you need to iterate. This L1 norm condition number will do something like that. It's in a slightly messier way. So here's an algorithm for L1 regression. I took this is L1 fever, I think it's called it. The 5 lines back for L2 regression. I cut and pasted, and I changed 2's to 1's. Right, so this is the same algorithm, except change 2 to 1. Using an L1 well-conditioned basis for A, construct an important sampling distribution. 2, randomly sample a small number of constraints, solve the L1 subproblem. If you do that, you get a 1 plus, this is something we had about, we originally did it in 2006, about 8 years ago. You get a 1 plus epsilon solution with that algorithm. And it only takes m times n to the 5th time. So this was a nice result. We sort of liked it at the time, and we understood what was going on a little bit better, but we shelved it because it clearly wasn't going to be implementable, let's say. But since 2006, we can make this algorithm run much, much faster in RAM. So Solar Woodruff have something called a Cauchy transform that allows you to reduce that mn's to the fifth down to mn squared with some log terms. You can use a Hadamard-based, the fast Johnson-Lindenstrass, a Hadamard-based version of this. You don't use Gaussian random variables inside the fast Johnson-Lindenstrass. You use Cauchy random variables to do that in mn log n time. And actually, remarkably, Jean Remain, a student of mine, and then Solar, and then Fox and Woodruff sort of in parallel. You can extend the sparsity time embedding algorithm for L2 regression to L1. And you can get an input sparsity time algorithm here. For L1, it's messy, so there's an extra log term. It's input sparsity times a log factor. So you can make this algorithm run much faster in RAM by approximating the leverage scores or performing an L1 projection. And depending on whether it's dense or sparse, it's this mn log n, or its number of non-zeros times a few log factors, which are a little bit worse than L2. And you can make this algorithm work in higher precision at RAM by coupling it with an iterative algorithm. So the basic idea here is what we talked about before. You construct a basis, solve the sum problem. I want to talk in the last few minutes just a little bit more about the iterative algorithm here. So L1 well-conditioned basis. I said Q is a nice basis for A. Here's the definition of it. If you just want to solve the subproblem, construct the basis, solve the subproblem, done. That'll work in L1. In fact, the basis has a niceness measure. It's not as nice as Q. It's a little bit messier. And you can have kappa is a condition number. And there's a trade-off between running time and condition number. So there's a bunch of ways to construct the basis. In general, as you go down along here, you get faster in terms of runtime. And as you go down along here, you get worse in terms of niceness. The condition number is a little bit worse. And in fact, something in the middle is the thing that is going to perform best on practice. Because you need to do something at the front end that's fast enough. But you need the niceness to be nice enough that when you couple and iterate, it's good enough. So there's an issue about constructing the basis, and then there's an issue about iteratively solving. How are we going to iteratively solve? So you can use subgradient methods or gradient methods, or there's a bunch of things that are going to be 1 over epsilon. But we really want the log of 1 over epsilon. Maybe times some other factors, because L1 is a little bit messy, but we want the log of 1 over epsilon. How are you going to do this? So you use something called the ellipsoid method. The ellipsoid is something that theorists love because it's polynomial time in the worst case, and no one else uses because it doesn't perform so well. And you can use something called the method of inscribed ellipsoids, which is a randomized interior point cutting gate plane method that's going to be related to that. So we're using a variant of the ellipsoid method here for the iterative algorithm. Now, why don't people do that in RAM? Because they can. They don't do that in RAM because there's an extra factor of n to the 3/2 work that you have to do. N is the low dimension, so that isn't going to totally kill you, but it's a lot. So it's an extra factor of 100 work. But the number of passes we need to do is something times log of 1 over epsilon. So how does that extra factor of 100 work correspond in practice? You can actually relatively cleanly map what we're doing the random sampling to the map and reduce step of MapReduce. MapReduce is the wrong way to be doing a lot of these iterative algorithms. I'm not going to have time to talk about this. Spark is a way, if you're familiar with that, there's a bunch of things that are particularly maintained in the states, so you may be able to get around some of the iterative algorithm issues, but for here we're going to be doing that. But just FYI, I mean, you shouldn't be doing iterative algorithms with MapReduce. So you have a map stage and a reducer stage. Note that multiple subsampled computation solutions can be computed in a single pass. You could be doing a bunch of things in parallel. So it performs well. Construct ellipsoids. What if you want to construct multiple subsample solutions? So what you need at each step of the iteration is a function value and a gradient. So, write a single query of a function value and a gradient or something like that. If you want multiple ones, replace the little x with the big X and call that a matrix. And it'll go through, right? Now you can do that in RAM, but if now instead of having an x be a column, it's a matrix of size 100 times whatever the dimension is, move through that, that's a factor of 100 more work. That factor of 100 more work you can do now in parallel. So it costs you nothing. So what do I mean when I say it costs you nothing? So just to give you numbers, 10 to the Hadoop cluster, A is 1/8 of a terabyte, so large but not obscene, but you get similar numbers if it's slightly larger or smaller. Single query. This took us 282 seconds. Let's do 100 queries. A factor of 100 more work. The clock time now, instead of being 280, is 320 seconds. So it's not free, but almost. So here we're going to, again, the same way as L1, the details are going to be different, but the same way as L1, we're going to use an iterative algorithm that's worse in terms of clocks, but much better in terms of communication. And the y-axis here is probably too small for me to read, never mind you. But you can get, there's some other issues I'm glossing over in terms of getting a good initial condition, and you can do a bunch of you can do a bunch of these in parallel, and at each step sort of annoys and get a slightly better iterate than just the one. So you don't have to just compute the 100 in parallel. You can average them in a certain way, and think of it as I don't know exactly, but think of it as 3 or 4 or 5 digits rather than 1. So you don't have 10 digits of precision. It's medium precision. So with that, let me wrap up. There's a bunch of things here in quantile regression, but I'm not going to go through. Quantile regression is sort of an extension of L1. If you think of L2 as a quadratic well and L1 as a B, quantile regression is a B that's sort of shifted to the side, and it allows you to get not just the means and the medians of L2 and L1, but the full quantile distribution of your model. Same ideas would go through. Use the L1 processing at the front end to get the L1 well-conditioned basis, and then instead of solving the subproblem that's L1, solve a subproblem that's quantile regression, and then compare back with the original problem. This is roughly how the quantile extension goes. And that was actually a nice test case for seeing how the various parameters played off each other in terms of getting a slightly faster algorithm versus slightly better basis in terms of condition of that thing, as I glossed over, but mentioned we had all these trade-offs here. So let me wrap up. So I was talking about randomized linear algebra. We're using randomization at various points, but for doing random projections or random sampling, to take linear algebra algorithms. So linear algebra algorithms appear sort of as a bread and butter in a lot of large-scale, small scale, but large-scale machine learning and data analysis applications. And so the question is, can you take, sort of all of small-scale machine learning, publication venues like NIPS and ICML and so on, where this sort of is totally bread and butter using matrix computation only. What fraction of that will scale up to be doing computations on a terabyte of data? And the answer is, not a lot, probably. So what little bit fraction of it is here, and then can you scale all that stuff up? And the idea is, when you can do things at a scale orders of magnitude larger, some easy things become hard, some hard things become easier. Which of those easy things are now hard? Don't do them. Which of those hard things are now easier? And you should be doing an ellipsoid method or a Chebyshev-centered method, and who knows what else to control communication and optimization and linear algebra algorithms in general. So I talked about least squares, least absolute deviations. I already mentioned quantile regression. These are nice test cases. And sort of the take-home message is, at a high level, the algorithms work the same as they work in RAM. But when you go parallel and distributed, you want to worry about communication, so you work with variants of the algorithms that have more computation, but much better communication profiles. So you saw that in MPI with the Chebyshev simulator, and the method is the method of describing ellipsoids and multiple queries. And those are just the tip of the iceberg in terms of looking beyond flops for sort of large-scale matrix computation in these parallel distributed environments. So with that, I guess let me wrap up. And thank you for your attention.